Today we have Dr. James Shanahan of the Church and Duncan Group at UC Berkeley. James leads organizations through digital transformation, from strategic planning, defining high-grading product and service portfolios, for large-scale data science and AI pipeline development and deployments for retail, digital advertising, and search. Previously, he has founded several startups and has held appointments at AT&T, NativeX, Xerox Research, and Mitsubishi. James received his PhD in engineering mathematics and computer vision from the University of Bristol in the UK. So I'll let him take it away.
All right, thank you very much for the kind words and introduction. And first of all, welcome everybody to this MLOps conference 2021, and welcome to this talk. And today I want to tell you about how computer vision and object detection has been revolutionized by deep learning approaches, both in a 2D world and in a 3D point cloud world. As introduced, I'm based in San Francisco Bay Area. I teach at UC Berkeley, and I also consult in artificial intelligence data science type projects. So now that we got the formalities out of the way, let's talk about computer vision. Computer vision is a field of artificial intelligence that trains computers to interpret and understand the visual world that surrounds us for a variety of exciting downstream tasks such as self-driving cars, checkoutless shopping, smart cities, cancer detection, and more. Now, though the field of computer vision has been revolutionized by deep learning over the past decade, today we're going to focus on the subfield of object detection, which has also been revolutionized by deep learning. So when we think about object detection, we're focusing mainly on, so I'm hoping you can see the screen clearly. So the goal of object detection really is to predict a set of bounding boxes and category labels for each object of interest in an image or in a point cloud. And here we've got an example. We've got two objects of interest. We've got a person and we've got a bicycle. And our goal here is to draw a bounding box to outline where this object exists and also to associate a label and a potential probability. So we're interested in the what and where in terms of object detection. So if we look at the field of computer vision in general, we'll see that it's transforming many industries as we start to instrument with cameras and LiDARs and other types of visual sensors. So fields from consumer health, finance, transportation, government, and retail are being transformed. So when it comes to object recognition and computer vision, one of the most common tasks that leverages computer vision is unlocking your phone with your face. Checkoutless shopping is also becoming pretty much a popular application, with many retail organizations adopting such strategies. Self-driving cars is a big user of both 2D and 3D object detection. When it comes to satellite imagery, we see many applications as well, such as figuring out where roads are using satellite images. So counting objects is also an important aspect or application of object detection. And when it comes to images, we can use RGB images, we can also use thermal images, and there are many applications in healthcare as well. So this is an example of breast cancer detection, and when we look under the covers, we see many keywords like RetinaNet, MobileNet V2, and we'll get into some of these architectures momentarily. So there are many fun applications as well. This is the Face app, where we can just take a face and imagine how we looked younger or older, and so on. Then there's the world of deep fakes. And of course, let's not forget the 3D world, where we're trying to work with maybe point cloud data, 3D data to recognize objects. So if you wanted the executive summary, this slide here could serve as that from a 2D object detection perspective. So here we have, on the x-axis, we've got time. In addition, so we're going from about 2012 up to 2021. And in between here, I've peppered the x-axis with different approaches to object detection. On the y-axis here, I've got the mean average precision. It's a metric of how good we are in detecting objects of interest. And this graph here was constructed based upon an evaluation on the COCO Object Detection dataset. It's about 200,000 images with about 5 or 6 objects per image that you want to detect. And there are about 80 classes of objects that we're interested in detecting. And when we look at the mean average precision for the 80 classes in this Microsoft COCO dataset, then we see that in the pre-deep learning era, we were getting about 5% mean average precision. And if we fast forward to today, we're getting about 58% mean average precision. That's a 4x improvement over the past, let's say, 7 or 8 years. So pre-deep learning era, we were looking at very simple approaches. They were working on derived features and support vector machine type classifiers. And some of the things that are interesting about this current graph here is that we have a variety of approaches, and these are all deep learning based approaches. And we can partition these deep learning approaches into a number of different categories. So in black here, we have 2-stage models to object detection. In blue, the blue bars here corresponds to one stage or single stage detectors. And then over here on the right, we have a new breed of detector, and they come by way of transformers. And that's right, transformers have arrived finally in computer vision. Last year was one of the first papers by a group at Facebook. It's called the DETER approach to object detection with using transformers. And in the meantime, there's been a number of exciting developments in the transformer world as it is applied to object detection. So this SWIN-L approach from Microsoft is a very exciting development, and this is a relatively newcomer here. So over the years here, in terms of deep learning approaches, we're seeing ourselves transition from 2-stage models to 1-stage models, and then we're transitioning into this mode of anchor-free approaches as well. So these might all seem a little bit double Dutch at the moment, but hopefully we'll get a chance to understand some of these terms as we go through the presentation. So all in all, we've made some massive progress over the last 5 years in terms of object detection. And here's from an academic perspective, there have been a number of exciting papers that one should be familiar with when it comes to object detection. And so pre-2010, there were a lot of really great approaches to object detection in computer vision, but they largely were around feature engineering and some very simple machine learning approaches. And it wasn't until 2012 when AlexNet architecture was introduced by Alex Tchaikovsky et al., where they were doing image classification. They also applied this AlexNet architecture as a backbone to object detection. And this kind of triggered some very exciting developments, not only in image classification, but also in object detection. So I should mention that over the years, a lot of very exciting data sets have been developed and put in the public domain. So Pascal was VOC was an object detection and classification data set that was developed by a European project, and that served as a sort of a benchmark so that people could compare their different approaches. ImageNet was introduced in 2009. We've got about 1 million images here, 1,000 classes, and there's also an object detection track as well associated with this database. And MS COCO was introduced around 2014. So these data sets serve as as ways to demonstrate your approaches. And in the meantime, other databases of images have also been introduced. OpenImage is one of the big ones that stands out here, with millions of images and hundreds and thousands of categories of labeled data. The interesting thing about OpenImage is that some of the data has been labeled manually using humans, and some has been labeled also automatically using machine learning approaches. So it's kind of a hybrid labeling strategy. So in terms of how we want to break down these contributions over the years, as I mentioned, there are these two-stage models, single-stage models, and then there's the anchor-free transformer-based approaches. So I'm just going to drop some buzzwords here. You probably have seen these out there in the literature, and there's RCNN, and there's a family of RCNN, region-based convolutional neural networks, that have started back in 2013, and they keep on going here. And so the most recent version of this is Cascade RCNN, and then these are two-stage models to object detection. And then we saw the introduction of single-stage models when we talk about YOLO, and the YOLO V1, V2, V3, V4, V5, and we see that YOLO is kind of a very YOLO V1 is a very naive approach, but very interesting and pretty awesome in some ways because of its simplicity. But YOLO V4 has stepped up recently as well as really a very powerful approach to object detection, and it incorporates a lot of the learnings from other approaches that are presented here as well. And Retina-Net is another single-stage approach to object detection, and this is a landmark paper that introduced a variety of ideas, including building on feature pyramids, and also a very interesting loss function based upon focal loss. And as I mentioned, the anchorless and transformer-based approaches are based upon Swin and Dieter, and there's a center point approach, which we'll talk about later. So when we think about object detection, we think about sliding windows, and this so I want to kind of step back in time here just to give you a sense of what's under the covers before we move on here. So when we look at an image, we see pixels, and the idea behind sliding windows is that we look at this image here, this section of the image here is a window on the image, and we ask certain questions of this window. Is there an object, and where is the object in this image? And so then we slide the window across, and I apologize, the animation is not working. And we basically take this window, slide it across, and slide it down, and in each of the windows, we ask certain questions and try to answer them. And so this is the idea behind the early approaches to object detection pre-deep learning. And typically what we had there was a 5-step approach to object detection. And we'll see that these 5 steps are important not only here, but also in a deep learning world as well. And they are, all these steps have been pretty much integrated into deep learning approaches. And so here, one idea here is the image pyramid, and the idea here is to take your original image and then downsample it based upon different levels of resolution. And that allows us to look at the image and objects at different resolutions, and it helps us from a detection perspective. So the idea then is to take these images at different resolutions and then slide windows over these images. And in this case here, we have a window here, and we take this window from the original image, and we construct a feature vector. It could be simple RGB vector, or it could be more sophisticated histogram of oriented gradients feature vector, which is a more sophisticated feature that's looking at a gradient edge information. And then we pass this vector along to a support vector machine, and then the support vector machine says, hey, I found an object in this window, yes or no. And obviously this pipeline here operating at different levels produces many detections. And so here are some of the detections that we get for this image here. These are all these red boxes here correspond to objects that are of interest. And so then we have this post-processing step called non-maximum suppression, where we suppress images that overlap, or regions, or detections which overlap to a high degree. And we end up with these candidate detections here. So this is a 5-step pipeline, and this pipeline is very sophisticated, but you'll be happy to know that we've made our way down to just a single step by way of the transformers and various other architectures. So, like I mentioned, this is just a more graphic representation of this, and so deep learning approaches to object detectors there are two principal families here. There's a 2-stage detector and 1-stage detector. This 2-stage detector involves basically taking the original image here and then finding where are possible areas in the image where there might be objects, and having kind of isolated those areas, then we take those areas and figure out what is the object in that area, and maybe also can we have a tighter bounding box for that area. And so this is our 2-stage detector. It's kind of localizing where are objects, and then going in and isolating the class and the location of the object. Whereas the 1-stage approach is saying, I'm just taking the original image and I'm pushing it through a convolutional neural network, and then I'm operating at different levels of resolution. Notice the pyramid here. And then I'm trying to figure out where the objects and classes are located here using this single-stage approach. So faster RCNN is a good example of this. Then we have these single-stage detectors. And here are some of the approaches, 2-stage and single-stage approaches. Now, a state-of-the-art approach for the 2-stage approaches is the Cascade RCNN. I won't bore you with the details. And so if you're new to computer vision, then I think that you need to really look at YOLO V1. It's a very straightforward approach. It's got a multitask objective function, and it's a single-step object detection approach. And the idea is very simple. We take our image here and we break it into different regions or windows, and then we operate on those windows after. So we take our image, push it through a convolutional neural network, and we end up with this feature map here, where it's a 4x4. Each of these cells in this feature map maps back to the input image. And then we actually answer questions based upon this local area of the image. And so again, you see the idea of windowing here. And again, it's important if you want to get into the technical details, into the weeds of object detection, then this is a great place to start, where we get to look at very complicated loss functions. We see very straightforward representations of this network here in PyTorch. And so in terms of the big breakthroughs in computer vision have come by way of these windowing techniques and these pyramids. And this made its way into RCNN. And when we think about RCNN, we think about an architecture that is made up of a number of different components. So we think of a backbone architecture, where we take our original image and map it down into different feature map representations. Then we have this idea of a neck, where we're doing certain transformations of these intermediate feature maps. And finally, we attach a head, and these are the prediction heads for saying what kind of class of object do I have here, and where is the object located. And so when we think of the world in this way, then this opens up a whole bunch of exciting possibilities. And so This is RetinaNet, and so this is efficient det. This is one of the state-of-the-art approaches to object detection, and this has been taken a few steps further in the last few months. But the idea here is that you got your backbone, you got your neck, and then the neck here, you have these repeating components for the neck before having the head. And so the nice thing about this approach is that we can have different levels of complexity. And so here's D0 to D7. And so these models, this is a very simple object detection efficient detect model. And this is a D7 is a very high powered, very complicated with many parameters. So, and we'll talk about that in a moment. So when it comes to object detection, there are some images in the COCO database that we do really badly on. And here are examples of images. So this is one here, there's a train. And so the problem here is that the bounding box for the train doesn't really fit with some of the prototypical bounding boxes that we're looking for in objects. And so to overcome this, people have introduced this center point approach, point-based approach to object detection. So we look at points in the image and find bounding boxes based upon those points. And this was some recent work. So some of the most exciting work that has been introduced here is based upon transformers. And I want to mention here, I want to switch to 3D for a moment. And this is an exciting piece of work from called RAND LA-net. It's for 3D point cloud object detection. It was presented last year at CVPR, and 3D object detection is really hot area in construction, in autonomous vehicles, and so on. And I think that you know, if you're getting into the field of computer vision, then it's important to go a little bit deep. And so here's a great textbook here that Alex Smolo and team at Amazon have built. And this book is nice because it's built on code that each chapter is written in Jupyter Notebook, and there's code and challenges for you. And here's one challenge here, just to build a single stage detector. And I also have a collection of notebooks for computer vision to get you going as well as in deep learning basics. So the bottom line here is that we've come a long way in the last few years, and some of the exciting approaches here are the transformer-based approaches, the anchor-free-based approaches, the efficient det approach, which I'm going to talk about just now. The efficient det approach is really nice because if you want to deploy models in production, you only have so much memory. So if you're looking at a cell phone here, I can't be shipping a model that's 500 meg in size. I need to have a small model. So if you look at efficient det here, we see that the D3 version here has 21 million parameters, and that's a kind of that's a reasonable size model that you could deploy on a mobile device. Whereas if you want more high-powered detection, here's the COCO average precision here. If you want to get some really high accuracy, then you need to start using more high-powered models that require a lot more compute power. And so the bottom line here is efficient det is an amazing approach. It's pretty straightforward. And not all models are created equally. And I guess when we compare object detection to natural language processing and using transformers there, here we have the GPT-3 model, 175 billion parameters, whereas efficient det is 50. It can be tens of millions of parameters. So we've got a long way to go in computer vision to catch up with this type of representation. So thank you very much for your attention. And if you have any questions, I would be happy to field them right now.
Yeah, thank you for the great overview, James. So just kind of briefly with some questions. Kind of commenting on, can you comment on transformers and how they're changing, let's say, how CNNs are used, convolutions are used as kind of a prior for CNNs, and kind of like how that's driven a lot of the progress for deep learning the last, let's say, decade. Transformers seem to have kind of you're no longer kind of assuming that that kind of those kind of parameters. Do you think that that means CNNs like will still have a role kind of going forward, long term in computer vision, or kind of what's your opinion on that?
Sure, I think it's a great question, and it's a hot topic. And so last year, some folks at Facebook made a transition into transformers, and they introduced this detection transformer DETER. And so if you look at the architecture of the DETER detector, then we're looking at a backbone that is still convolutional in nature. We're taking our original image and we're converting that into feature maps that is then flattened and given to the transformer encoder and decoder. And so I think there's a lot of synergy between convolutional neural networks and the transformer architectures. And as I mentioned earlier, in the last few months, we've seen a whole bunch of new papers and approaches that build on this transformer idea. And I think the most exciting one of those is the SWIN transformer. It's a hierarchical transformer from the folks at Microsoft Asia. And this approach has blown away the competition on the MS COCO dataset. So I think that there's a lot of promise in keeping both around, and so I would encourage you to have a look at the transformer approaches. There's a lot of mileage left, and I think there's the complexity of these models is still pretty high. So we need to figure out how to address that, I guess.
I see, and I guess in terms of kind of like the self-supervision tasks, that's somewhere where like transformers have really shown self-supervision to be effective. Where do you see kind of like, how do you see that evolving? Like if you have a lot of kind of unlabeled data, but you're still applying self-supervision to it, what are like the most kind of effective tasks, and how will that evolve going forward?
So, so for unlabeled data, so I guess one of the big breakthroughs in the last, I don't know, maybe a couple months, has been around cut and paste and learn. And so previously we have had, so in training a computer vision model, whether it's classification or detection, there are lots of tricks you bring to bear. So one of the tricks we have used a lot is that of augmentation, where we say, take an image, scale it, crop it, transform the colors and somehow, that augmentation step has been critical in improving the performance accuracy, prediction accuracy of various networks. So over the last few months, folks at Google have said, okay, well, this works well. What else can we do with this idea of augmentation? And so what they've done is a really clever idea, and that builds on some previous work from 2018, and that is to take images and objects and to cut and paste objects from other images and put them into your current image. So you're augmenting your images with cut and paste objects from other images. And then you might blur those or jitter those as well. And so when you do this, you see some dramatic improvement in learning and generalization. Right. So you're making more from your data.
It's a data augmentation technique, and I guess in terms of transferring kind of the transfer learning that occurs between a model that's kind of been self-supervised on a lot of data and then fine-tuning it to a specific task, that seems to be quite effective, as in the kind of NLP case.
Sure, absolutely, yeah.
Right. I guess in terms of kind of like progression of YOLO from V1 to V4, what have you seen kind of the progression of ideas that kind of evolved it?
Yeah, so I really love YOLO V1. It's a love-hate relationship in the sense that the approach is very simple. So it's kind of relatively straightforward to get your head around what's going on in terms of your multitask loss function. Now, how has YOLO V1 evolved over the years? Well, first of all, the loss function has changed. Then the idea of, as I mentioned earlier, the sliding windows approach. That sliding window approach has also evolved dramatically as well. And so we have this idea of anchor boxes that kind of basically stand for sliding windows. It's an efficient way for us to encode sliding windows. And then we have this idea of pyramids. And so YOLO, the YOLO architecture has basically said, hey, let's try to learn from what other people are doing. And so in essence, it's like RCNN. It's pyramidal in shape. So we talked earlier about the backbone, we talked about the neck, we talked about the head. And so YOLO V1 to V5 has sucked in all of those key ideas and also modified its loss functions. And the big focus of YOLO is to keep things efficient. And they've worked hard at kind of maintaining that. So I think that YOLO, the YOLO architecture framework is kind of it's a summary of what's happening in the field of computer vision, I guess.
I see. So they're kind of combining all the various kind of state-of-the-art techniques. But what if you're comparing kind of something that's efficient from an architectural design point of view versus something that's been kind of compressed and sparsified or distilled, where it's kind of like it's like the architecture is complicated, but it's heavily distilled. Is there comparable kind of efficiency between those two, or let's say like yeah?
So I guess the trade-off is always architecture simplicity versus getting good predictive accuracy in terms of detection and classification. And so we've seen a lot of work in building out more efficient backbones, as well as efficient necks. And then, of course, the heads are kind of constant for pretty much most approaches, especially in the single stage detectors. So when it comes to, so I talked about efficient data as kind of a nice place if you're thinking about deploying something to the edge, where you only have, let's say, tens of meg to deploy the model. Then, so anyway, I guess the trade-off here is complexity and compute power requirements versus predictive accuracy. And so I think the efficient det provides a really nice way of looking at the different levels of computational requirements versus predictive performance. And they've done a really nice study on doing this. And of course, you can swap out the different components of the backbone architecture, the neck and the head. And so people focus on using mobile nets and the different versions there as backbones, combined with a pyramidal type head or neck, sorry. So it's a trade-off, and there's no one size fits all here. It's down to how much memory you have on your edge device at the end of the day.
I think. Can you hear me now?
Yeah, great.
Okay.
Thanks.
Apologies for that. Just the camera cut out. So I guess in terms of deploying to edge devices, can you comment kind of on what kind of models work best, kind of in kind of these domains in your experience? Yeah.
So yeah, so we talked about YOLO V1. I mentioned SSD, this single shot detector. And so these architectures are super sweet because they're fully convolutional. That means that we can go from, well, YOLO V1 is not fully convolutional, but you can make it fully convolutional. So what does it mean to be fully convolutional? It means that we take our input image, and all we're doing is taking that input image, and pretty much we're downsampling all the way to the last output layer. And then we're making predictions there. So if we have a fully convolutional network, then that's super attractive from a deploying to an edge device, because we can, before deep learning, there was a whole field of computer vision, and there's a whole plethora of chips and libraries that have been developed that cater towards fully convolutional operators. So in the old days, we had all these edge detectors and texture detectors, and so they could be parallelized, and so if we have a fully convolutional network, means that we can start off with our input image, and we can start dividing and conquering immediately. And so if we have, like, say, 100 threads on our edge device, then we can partition our image into, say, 100 zones and proceed. We put each little zone or window in the image into its own little swim lane, and it proceeds from start to the finish, the output layer, and we can make a prediction. So having a fully convolutional neural network is super attractive. And unfortunately, with the more recent architectures, we have dropped some of this fully convolutional stuff, because we have not just one output head, we have multiple heads. Now, having said all that, we can still make those heads are fully convolutional paths through the network. So when it comes to deployment on edge devices, we can leverage this fully convolutional layer nature of the networks. And so the mobile.
Sorry, are you leveraging it in terms of so let's say edge devices? You're assuming that it's kind of CPU based, or there's some specialized kind of accelerator like FPGA based, or is it GPU? Is that something that can be deployed? Like, what is the typical kind of processing that, because you're saying kind of the fully convolutionality of it is what is allows it to be optimized on that kind of hardware, but is it always just CPUs? Or?
No, I think all of what you said. I think that you have a variety of devices, but I think if you try to keep your network fully convolutional, then you can leverage all of these devices. And that's sometimes very attractive, because maybe you can't afford to have the GPU chip. Maybe you're using an FPGA type chip. Maybe you're using a CPU, and so it really depends. But keeping everything convolutional is very attractive, and that's what GPU cards really leverage as well. But if you can't, then you need to start thinking about simplifying your architectures. And the published architectures are really good, but you are looking for using lots of different tricks in order to get your model down to a few meg or tens of megs. And so that can go from anything from downsampling the original image to a resolution that can still give you adequate predictive accuracy. And then also you may also trim back the architecture, so that involves retraining, some transfer learning and retraining, but it's just a trade-off.
Right. I guess in terms of kind of other types of let's say if you're processing video data. Like a lot of, let's say a model can be trained in kind of the individual sample, like the individual frames of the video data, but there's also kind of the relationships between frames, correlations between pixels and between frames that can be very informative, maybe about like the physics of a scene, or there's kind of some implicit knowledge that the model can kind of capture. What do you see in terms of literature and how kind of this kind of the time kind of nature of the data, how that's kind of leveraged by the model, or how that's captured on?
Yeah, so this is kind of definitely a very hot area, and so if we can track objects over time, through time, that's very attractive. And so some of the tricks there are that we try to register different points in the successive images. And if we can do that registration easily, quickly, then we can afford to be, in terms of recognition, object detection, it makes our detection algorithms so much more efficient. And so if you want to maybe learn more about this, then one of the areas that kind of uses this a lot is autonomous vehicles. And so it's kind of this object tracking module in autonomous vehicles that that will have a lot of the descriptions of different approaches that are, so it's a good starting place to kind of figure out what works there.
I see. Fantastic. I guess maybe one more question. I'm going back to edge devices. For kind of successful, what do you see as kind of a successful kind of framework for deploying to, or the most successful for deploying to the edge? Like if you had, let's say in your own work, if you had to design, develop something that can kind of deploy easily and you can kind of update, and like the kind of pipeline is kind of very, what do you see?
So in terms of frameworks, I used to think TensorFlow was the business, and it still is. It still is pretty awesome, and it's got a wonderful and there's TensorFlow Lite, and so there are lots of tools that help you deploy models to the edge, because you're not going to take your research paper model and just shove it out to the edge. You're going to do various things like compressing the models. You're going to not be looking at doubles. You want to get floats, maybe ints. You want to so you're going to transform your model into a much simpler model and hope that you still get good predictive accuracy. So TensorFlow has a collection, has a pipeline, a workflow that you can follow to get stuff out into the edge, which is pretty awesome. I like PyTorch a lot, and PyTorch has come a long way. It's still working through some of these deployment issues, and so I think TensorFlow is much more established at getting things to the edge, but I think PyTorch is catching up very quickly.
I guess because there's always this tension as a kind of a researcher and a practitioner. You want a fast prototyping of PyTorch, but you also want kind of the ease of deployment of TensorFlow. Do you think in terms of kind of interoperability of like Onyx and kind of these intermediate representations that allow you to kind of export maybe from one to another, is that something that you see a lot of utility for, or is it just easier to have everything streamlined in one framework?
It's kind of nice to have a single framework, and this interoperability is really attractive, but it sometimes introduces issues, and the Onyx framework is definitely very nice, but it's pretty new as well. So there are some challenges sometimes. So I think that keeping to a single framework is really desirable, and especially when you're in production mode, when you want to have quick turnaround times and you want reliability. And as I mentioned, I think TensorFlow provides a lot of that, though I prefer PyTorch as a framework for doing deep learning type stuff.
Of course, yeah, I can say I definitely agree there. Well, I've learned a lot from this presentation, as have our audience. So thanks for your time, and I appreciate your insights.
Thank you very much. Thanks, Ali. Thanks, David.